Now once we understand that, let us see why the extension does not happen. As I said, to counter the extension of the rods, these walls now exert compressive forces on the composite rod at both ends. So, at the left end, the compressive force given by the wall on rod number 1 is acting to the right. Let me call this force as F. And at the right end of the composite rod, the wall is exerting a force, compressive force of equal magnitude acting to the left on rod number 2. So I might call this force as minus F. And these two forces have to be equal in magnitude and opposite in direction because the whole composite rod is in equilibrium between these two rigid walls. Now if we consider each of these two rods individually, each of them is in equilibrium as well. It means for the equilibrium of rod number 1, if there is a force F exerted by the wall to the right, there must be another compressive force exerted by rod number 2 to the left. So this force is minus F acting on rod number 1. And similarly, for the equilibrium of rod number 2, if there is a force minus F acting to the left by the wall, this rod number 1 must also have exerted a force F onto the right on rod number 2. So you see, it is not only a pair of forces F minus F exerted by the walls at the two ends of the composite rods, also at the joining point, meeting point of these two rods, the rods are exerting compressive forces on each other of magnitude F each. Therefore, if I might draw the free body diagrams of the two rods 1 and 2 individually, let me show that separately here. For rod number 1 in white, the forces are a force of F to the right exerted by the wall and force of minus F directed to the left by the right side rod. That is rod number 2. And these forces are F and minus F. And similarly, for the FBD of this right side block number 2, here is a compressive force of minus F given by the right wall and a compressive force of plus F given by the rod number 1 onto the rightward direction. Both of these rods are now under compressive pair of forces, a pair of compressive forces. And because of that, they will suffer contraction in length. So on one hand, there is extension because of temperature rise. On the other hand, there is compression of both the rods because of compressive forces coming in the picture. So we might write down now, this is, I might write, we are finding out elastic compression of the rods because of the presence of those massive rigid walls which stop any possible extension. And for that, first of all, let's recall the formula for Young's modulus. Young's modulus is given by stress by strain. That is the magnitude of compressive force F divided by the cross-sectional area. One more data is given here, that for both these rods, the cross-sectional area is given to be capital A only. Okay? So, F by A is the stress, in this case compressive stress, divided by the strain, that is change in length delta L by L. This is coming out to be F into L divided by A into delta L. By rearrangement, delta L, the change in length, is given by the formula F into L divided by A into Y. In this formula, delta L is standing for the change in length, F is the force, tensile or compressive, L is the original length, A is the cross-sectional area, and Y is the Young's modulus for the rod material. Let us apply this formula for the two rods once again. So, for the rod number 1, in white color, we might write down that the compression, this is, I'm writing the magnitude only, delta L1 dash, to distinguish this from the earlier symbols. This is the value of compression of rod 1 under a pair of compressive forces of magnitude F each. This is F into original length is L1 divided by cross-section area is A, Young's modulus is Y1. And for rod number 2 similarly, using the same equation, the magnitude of compression delta L2 dash is given by magnitude of compressive force, the same F only I have explained in the figures. F into original length is L2, cross-sectional area is A only, Young's modulus is Y2. So once again, adding up these two quantities, we are getting that the total elastic compression of the two rods under the effect of those massive walls is given by delta L1 dash plus delta L2 dash. This is F into L1 by A into Y1 plus F into L2 by A into Y2. If I take F upon A as common, I am getting inside bracket L1 by Y1 plus L2 by Y2. Just check this one. This is my question number 2. And once we have got expressions for total thermal extension possible and total compression under rigid walls compressive forces, this extension and the compression must be same in magnitude so that this composite rod doesn't suffer any change in length. Therefore, to get the value of this force, you have to find out here the force exerted by each rod on the other, and that is nothing but this magnitude F. So we just equate these two expressions 1 and 2 and could write down the extension is equal to compression in magnitude, that is L1 into alpha 1 plus L2 into alpha 2 into theta must be equal to capital F by A into inside bracket L1 by Y1 plus L2 by Y2. And it follows therefore that magnitude of the force F is coming out to be L1 alpha 1 plus L2 alpha 2 inside bracket into A into theta, whole thing divided by L1 by Y1 plus L2 by Y2. And this is the answer of this question. The magnitude of compressive forces exerted by each rod on the other is L1 alpha 1 plus L2 alpha 2 into A into theta by L1 by Y1 plus L2 by Y2. Let me quickly remember the different symbols here. L1 and L2 are the original lengths of the two rods. Alpha 1, alpha 2 are the expansion coefficients of the two rods. Y1 and Y2 are the Young's moduli of the two rods. Capital A is the common cross-sectional area of either rod, and theta is the temperature rise of this composite rod. This is the answer of this question.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.